I'm Franklin Harding. I am a software engineer. I've been working at a company called BillUps for the past year. I just recently quit. I did a lot of Go and Python and JavaScript there. I also am a huge FIRST robotics competition nerd, if anybody's familiar with that. I was on team 2733 in high school, and I mentor them still. And I also wrote the web CTF challenges for this event. So, hint, hint, talk about web vulnerabilities. So I want to start the presentation off with these two quotes from the Go Time podcast. The first one being, I feel like programmer laziness is the major cause of security issues. This is from Roberto Clappis, who does security stuff at Google. And this is kind of the core quote for my presentation. So the TLDR of these is we shouldn't be blaming developers for vulnerabilities. We should be blaming the tools they're using and the insecure architectures they're using, bad defaults, stuff like that. So we need to make it hard for developers to make mistakes. And we need to make it so that when they choose the lazy path, with which they will, that they choose the secure path incidentally. So it's becoming harder to mess it up. So let's go through like some common vulnerabilities that you might see in a lot of cookie cutter CTFs and stuff like that, and talk about why it's becoming harder for developers to write those vulnerabilities. So I want to start off with just a SQL injection. So this is an example of probably the simplest HTTP handler you could write in Go for receiving notifications from a SQL database. And it's totally safe from SQL injection. It would take more code to make this example vulnerable to SQL injection. So that's kind of the key pattern we're looking for here. It's really easy for developers to not write insecure code. And then, so memory and data race safety. So I'm going to talk about Go and Rust here because, in my opinion, Go is definitely the future of web services, and so is Rust. So with Go, the worst case scenario regarding memory management is that you're going to dereference a null pointer. There's no pointer arithmetic. There's no manual memory management. You have 0 values for everything, so you deal a lot less with pointers and like undefined variables in general. So nothing is really dangerous besides dereferencing a null pointer. And the worst thing that's going to happen in that case, if you have a web server, is it's going to cancel the request. Program's not going to crash. It's really not a huge deal. And then regarding like race conditions, so Go has an excellent race detector that's built into the toolchain. So you can build your program with the race detector enabled and start hitting it with like thousands of requests and see what happens, or you can write a bunch of really racy tests and then run those tests with the race detector enabled and see what happens. So you're really safe regarding, you might not be safe regarding data races, but it's really easy for you to detect that, and it's really built into the toolchain out of the box. And then with Rust, so most Rust code doesn't need, you don't need to use nullable pointers for mutability. And then if you need truly optional values where you might use a pointer in a language like Go, you can use an option monad instead. And with an option monad, you have to handle both the case where there is a value and there isn't. So that's a lot safer. You deal a lot less with pointers, and you have to handle both scenarios explicitly. And then Python and Node, not really even going to talk about those, even though they're more modern languages too, I think. You're not doing manual memory management. They're single-threaded, so assuming you're just running one process, one worker, you're not going to run into application-level data races at all. So here's an example of an HTTP service in Go. We have one endpoint that dereferences a null pointer and one that prints I'm still alive. So we hit that I'm still alive endpoint. We hit the dereference endpoint, and then we hit the I'm still alive endpoint. And this is kind of just to demonstrate that it's not a huge deal to dereference a null pointer in Go. So what's going to happen? Prints I'm still alive. We make it panic, and then it continues to work. Not a big deal. It can become an issue if you have things like cleanup that you're relying on and you haven't deferred those. But yeah, in general, not a big problem. So cross-site scripting and cross-site request forgery. It's a lot more common now to use the web storage API like local storage for storing tokens rather than things like cookies, which makes cross-site request forgery a lot less of an issue because you're not having your tokens sent along with every request by default like you would with cookies. It can make cross-site scripting more of an issue because now you're allowing JavaScript to access your tokens, which you wouldn't have with like secure HTTP-only cookies or something like that. And then regarding XSS, so like if you use the Go HTML template package, you don't really have to worry about XSS. It can still be an issue, but in general, it's safe by default. So like right here, I have some code, and all it does is it has a paragraph element with some data injected into the middle of the paragraph element, and I just run that with your XSS generic script alert 1. And if we run that, we can see it's automatically escaped. It's easy. It's secure by default. It would take more code to make this vulnerable to XSS. And then with modern web frameworks like Svelte and Vue and Angular and React, obviously, those are mostly safe from XSS. There are things like props being unescaped in React, or things like dangerously set inner HTML. But again, like this general pattern that the lazy path is the secure path is true for those modern web frameworks. Another thing I really want to talk about that isn't really a direct vulnerability is errors as control flow. One of my biggest issues with languages like Python and JavaScript is that you're dealing with errors as if every single error is an exception. So let's define exceptional really quick. Unusual, not typical. Is that what an error is? No. You can expect errors anytime you're doing anything over the network or anything with I/O. It's not exceptional. It should be part of the control flow of your program. It should be very hard to ignore what happens when there's an error. So Go follows that pattern really well with returning errors as values. And you can panic in Go when you have a truly exceptional condition, but you usually don't. So like in this example, we compile a regular expression with a constant value, and we know that's generally always going to compile. It's a constant string, we know it'll compile. So there, it makes sense to panic because it's an exceptional condition. But doing something like making an HTTP request, that's not exceptional. There could be a million things that go wrong there. That there could be like no host, like in this example, if I run this, there's no host. There could be, you could lose your internet connection. That service could be down. That service could be responding incorrectly. So there's a million things that could go wrong there. And I really like this pattern of using errors as control flow and handling errors rather than just assuming they're not going to happen. And then authentication and authorization. So Go has some extremely good standard library. They're called sub-repos, but they're basically standard library packages for OAuth 2. They're really easy to use. They're mostly secure by default as far as we know, and they're maintained by Google and used by Google. So that's for what it's worth, that's pretty nice to me. There's built-in support for common providers like Google and Slack and Spotify and GitHub, stuff like that. So you don't have to worry about implementing those yourselves or finding the endpoints for those. And you can easily use OpenID Connect for authentication for your service. So you don't have to be storing hashed passwords or whatever, or worry about interacting with the database for your authentication. You can just really easily use those standard libraries to use OpenID Connect to authenticate with other services and use that as your authentication. And then also, so JWTs are becoming a lot more common than just session tokens. And that definitely has some pros. It's a really easy to understand and use technology. It's pretty straightforward. It's just, if you're not familiar, it's basically just base64 encoded signed JSON. And it's a little bit more complicated than that, but that's the root of it. It's also totally stateless, so you don't have to interact with the database every time you want to check whether users should be authorized to do something, which is pretty nice. The less I can interact with the database, the happier I am. And you're writing less code, which is always great. So there's also really good library support for JWT in pretty much every language, but the point is, there's stuff that'll already do it for you. You don't have to worry about implementing it yourself. And generally, those libraries have pretty good assumptions. So I want to talk a bit about dependencies, and we'll talk about this later too. But I think it's not always a bad thing that developers install dependencies like crazy. People joke about the NPM ecosystem all the time, but in general, especially related to security, if a developer doesn't know how to implement something or they don't have time, it's good for them to just download a library that does it for them most of the time. We'll talk about why that's not always true, but we also, we get what we ask for with dependencies now without having to vendor them or do anything like that. Thanks to immutable proxies like npm and proxy.golang.org with Go modules. and then your lock file is having checksums. Like, you know that the code that gets built on your build server is the code that you had in mind when you were developing the code. And then also Dependabot. So if you're not familiar with Dependabot, what it'll do is scan your GitHub repo, and anytime it discovers that one of your dependencies has a vulnerability and it gets patched, it'll automatically open a pull request to your repository to update that dependency, and it'll specifically tag it if it's like related to security. That's really nice because it makes it a lot easier to handle your dependencies. You don't have to like worry about somebody manually going through those every once in a while and keeping stuff updated. And it's especially nice that you can just have it only care about security-related stuff. It's also free, even for private repos. It's really easy to set up, which is great because, again, it needs to be easy or nobody's going to care about it. And there are also similar solutions if you don't want to go with Dependabot, like Renovate and Snyk and other services. So I want to talk about fuzzing a bit, too. Fuzzing isn't really new. We've had like AFL and stuff for a long time. But I think it's really cool that you can use fuzzers with modern languages like Go and Rust in like really easy turnkey ways. So like there is a Go package called GoFuzz by this guy named Dimitri. And it's very easy to use to fuzz your Go application. It uses the general pattern of AFL, which could be summarized as like using genetic algorithms to target high coverage code and find interesting code paths and provide random inputs to those and see what happens. It's, again, like fuzzing isn't new, but it's great that we can use these with these new tools, and yeah. So the more exciting part of this presentation, it's still easy to mess it up. So while it's great that we talked about all these common vulnerabilities and how new tools are preventing those common vulnerabilities, now we're going to talk about these new tools and what new vulnerabilities they have. So NoSQL. NoSQL databases are great because you don't have to worry about SQL injection, right? So if you're using like MongoDB and Node without like TypeScript or something, it's really easy for you to provide the wrong payload to MongoDB and mix your data and code. And that's kind of the root of SQL injection. So like here we have a payload, which is what we would expect, which is like username, and then John is a string, and then username and an object greater than empty string. So it's like or 1 = 1 in SQL. And if you're not checking that type and you just provide straight from the payload that value to your MongoDB call, you're going to mix data and code. And then also, so key collisions are a huge thing that I feel like isn't talked about very much, but with a lot of modern like key value stores like S3, Redis, DynamoDB, stuff like that, it's a lot easier for you to create a schema for your keys that is vulnerable to key collisions and things like that, which obviously you don't want. It can allow attackers to view stuff they're not supposed to, or to override other users' data and do stuff like that. Whereas in a SQL database, you might have a bunch of columns that you would create a primary key for that's made up of those columns. With a NoSQL database or a key value database specifically, you have to create the schema for generating that string key from whatever primary keys you have, or keys you have in general. So JWTs are great, right? But they're also really hard. So Aaron Parecki, in his talk about hacking OAuth, talked about the none algorithm thing, which was huge a while ago, where you could just provide a JWT with the algorithm none, and those libraries would not do any verification of the expected algorithm, and so it just wouldn't validate the signature at all. So you could put whatever you want in that JWT. You could say you're whoever you want to be. You could say you're allowed to do whatever you want to do, whatever. And then also, a lot of libraries leave like validating certain claims up to the user of that library, which is a really bad idea because, like we talked about, we shouldn't be leaving things up to developers. People are going to misuse that, and they're not going to validate claims properly. And also, people sometimes don't realize, like, JWTs aren't encrypted, right? They're just base64 encoded JSON. So if you put confidential information in the claims of your JWT, anybody can look at that. You need to be really careful with what you're putting in your JWTs and not leaking information. Obviously, if you're leaking the user ID for like the user that's logged in, it's not a huge deal, but you don't want to put stuff in there that they're not supposed to see. People also will often use like extremely long-lived tokens that are stored insecurely. So like if you have a refresh token that's valid for 2 months and it's stored in local storage and somebody finds XSS on your app and gets that refresh token, they can print tokens for that user for 2 months. So like, and then also things like if you have a short-lived access token, if you have a long-lived access token, if something happens to the user, like they get their admin privileges taken away or whatever, and that token doesn't expire quickly, then they're gonna still be an admin for as long as that token's valid, unless you blacklist it or do something like that. Another common thing is like weak secrets and algorithms. So people don't realize, like even with like HS256, if you have a weak key, it's pretty easy to brute force that. And Auth0 wrote an article on that about brute forcing HS256. But in general, the TLDR is just, if you're using like a symmetric algorithm like HS256, just use a really strong key. Because again, if somebody brute forces your key, they can just make up JWTs that say whatever they want to say. So microservices are a really common architecture. Especially where I worked, we had a lot of microservices, and I found it's kind of like playing telephone with user authorization. So if you have like service A, which is privileged and can do pretty much whatever it wants to service B, and you have a user call service A, you need to be really careful about what that service A does on behalf of the user, because it's fully privileged to that other service, so it can do whatever it wants. And then if you're, kind of trying to proxy user authorization, that can be an issue as well. There's more room for SSRF, obviously, because there's more service-to-service communication in general. Like if you have a monolith, the only services you're going to be calling out to are like remote APIs and stuff like that. Whereas with a microservice architecture, you're obviously going to be making a bunch of service-to-service calls. It also might be harder to patch systematic vulnerabilities if you have like a vulnerability that's spread across a bunch of your microservices. Things like Dependabot help a lot with that when it's things that are relevant to like your dependencies and not your actual code, but it can be a pain in the ass to patch systematic vulnerabilities in your code itself. So dependencies, again, while it's great that developers aren't like, just writing their own code and implementing their own crappy solutions for stuff and they're installing stuff when they know they can't, it can also lead to a lot of issues because people will just install dependencies for everything, every little thing, like leftpad, for example. So a dependency, like a thing like Dependabot is great, but it's only great when a vulnerability is identified and the code is patched and it's released. So if you have a bunch of dependencies, there's gonna be unknown vulnerabilities in those dependencies that aren't patched. So the only way you can not have vulnerabilities in your dependencies is just have fewer vulnerabilities in your dependencies, is just have fewer dependencies. So literally unsafe code. So we talked about how it's pretty great that Go has this really safe approach to like memory management and stuff, but you still sometimes need to write like unsafe code and do things like pointer arithmetic or access raw pointers if you're like interacting with like C code or doing something like that. And in that case, all those things I said go out the window, right? Like we can do whatever we want with pointers. We can do pointer arithmetic. We can assign to arbitrary places in memory. So like in this example, we have slice A, which contains 4 values, and we slice off the first 2, and we slice off the last 2. And we find the pointer to the first element in that start slice, which is the first 2 values. We add the size of 3 integers to that, and we dereference that location and set it to 42, and we can start accessing other places in memory that would normally be outside of the bounds of that slice. So in this case, we change what's an end, even though we were just looking at start. So interoperability with like C systems is a great thing that Go supports. So with things like CGo, you can call C code directly from your Go code, which is great. But it can also lead to a bunch of issues because that C code and your Go code are sharing memory. So like in this example, we have this function dangerous, and all it does is dereference the pointer we pass to it after adding the size of 3 ints to it and sets that to 666. If we pass in that start slice that we had before to this, and then we print the end slice, we can see it's setting stuff in the end slice. So it's sharing memory with our Go code, which, yeah, again, all your guarantees about memory safety go out the window in that case. So what have we learned? Blaming developers for security vulnerabilities is flat out unreasonable for the most part. While like we should rely on developers to not do insane things for the most part, it should be very, very, very hard for developers to do insane things. And they're not going to want to do those if they're more effort than doing the easy thing. We also like see that pattern in a lot of newer tools like Go. So a lot of these assumptions that like we need to make it so, like an HTML template, for example, when you do something the lazy way, it's secure, and it's not vulnerable to XSS in that case. But we're not totally there yet. So even with tools like Node and MongoDB, like we said, like mixing data and code and interoperating with old systems like C systems, which is just something people need to do, but it still removes a lot of those guarantees. And then with microservices, like I talked about, there's a lot of room for SSRF and doing stuff that you're not supposed to, and confuse deputies and all of that. And yeah, that's it. Thank you guys.